And then
Can I get like more of this thin chalk?
so yeah, I heard Greg reference the new chalk. So we like that better than this thicker chalk.
Yeah,
I don't know.
It's closer to my European. Well, I have this, so maybe.
Let me see. This is what you like, the thinner.
Yeah, I like.
What is the word on it? I don't know where this came from. Higuerono.
Maybe it's like personal chalk. Okay, here's one more. I think I'm okay. Yeah.
Should we get started?
Yeah.
All right, let's get started. So, now Rychkov will conclude his talk on conformal field theory in more than 2 dimensions.
Yeah, I'd like to jump into my last subject, which is called embedding formalism. So it's kind of a way that we do computations in conformal field theory. It's a smart way, and okay, it's a pretty standard way that those people who are here experts on CFTs have seen most of it, but even for those people I prepared a cherry on the cake at the end that they might not have seen. So as in our first lecture, I mentioned that the conformal group is isomorphic to SOD plus 1, 1. And so the main idea is to consider a vector representation of SOD plus 1, 1, and inside this vector representation to find the conformal group, and that's how we will be able to generate effortlessly conformally invariant expressions like conformally invariant correlation functions. So that's the smart way to do it, which goes back to Dirac. And so explicitly what we are going to do is that we are going to introduce coordinates x1, xd, and 2 more coordinates xd plus 1, xd plus 2. So this is going to be our coordinates in r d plus 1, 1, and this is the time-like direction. So I will also introduce the light cone coordinates x plus minus, which is equal to xd plus 2 plus or minus xd plus 1. And the metric is the sum dx mu squared for 1 to d minus dx plus dx minus. So on this space, SOD plus 1 comma 1 acts very naturally. So the action is so x mu xm goes to lambda mn xn. It's the action of SOD plus 1 comma 1. And so now we would like inside this action to find the action of the conformal group. We would like to find the conformal transformations. And so we need to, since the conformal transformations act on RD, and here we have two extra dimensions, we have to get rid of these two extra dimensions without spoiling the beauty of this linear mapping. So the way to do this is, so we have to kill these two coordinates, and in order to kill the two coordinates, we do two things. So the first thing is that we are going to restrict everything. Restrict this action to the light cone, x squared is 0. And so that's a very easy way to kill one of the two coordinates, and it does not spoil anything because the light cone is of course preserved under the action of the SOD plus 1 comma 1. And but we have to still kill another coordinate, and in order to kill this second coordinate, we are going to choose, so we have this light cone, and we are going to choose a section inside the light cone. And this section is going to be given by the equation x plus, so the most general section is given by this equation, x plus equals some function of x mu. And so the picture that we have is the following. So we have this light cone, and we only work with the future light cone. So we have these coordinates x plus and x minus, and we have all the remaining coordinates x mu, and I have a section which I'm going to draw something like that. And so this is my section. So x plus is a function of x mu, and once I know x plus and x mu, I also know x minus, because everything has to lie on the light cone. And so now once I have this section, I can, so I have to make my conformal group, my SOD plus 1 comma 1, to act not on the light cone but on the section. And the way it's going to work is the following. So we take some point x mu. So I'm going to identify the coordinates x mu, big X mu, with the coordinates small x mu of my d-dimensional space. I take a point x mu, and the point x mu, so it defines for me a point on the section, and a point on the section defines for me a light ray. So from x mu I go to a light ray. So once I have a light ray, I act on it with my lambda mn transformation, and I get another light ray. And so I look at this other light ray, I look where it intersects with my section, and that's the final point of my action, x prime. So this is the prescription that I'm going to take for my action. Any questions about that? Okay, so now I would like to show that this action actually defines a conformal transformation. So what do I need to do for that? one of the ways that we define conformal transformations is in terms of the transformation of the metric on my manifold. So which metric should I look at? I'm going to look at the metric, a natural metric on the section is the restriction of the metric on the light cone to the section. So this is the natural metric that we are going to take. So the metric is given by ds squared equals dx squared minus dx plus dx minus, restricted to this section, x plus equals f of x mu, and x minus equals x squared over x plus. So this is some metric that, okay, I could compute it explicitly, but I'm not going to need it. So let me just write it like this, g mu nu of x dx mu dx nu. And so now I would like to understand how this metric transforms under this transformation that I cooked up. So let me make another picture, which I'm going to use to compute the transformation of the metric. So this is my section. So this is the point x. And now I'm going to take two nearby light rays, which are separated by some dx. And now I apply my transformation, which first of all I apply this SOD plus 1, 1. So x goes, so the point x on the section, it doesn't of course remain inside the section under this transformation, it goes somewhere else. So this interval gets transformed into some other interval. Okay, let me. So this interval goes here under lambda mn. But of course, the transformation, the Lorentz transformation in this ambient space is an isometry. So in the first of the two steps of my transformation, where I go from one light ray to another light ray, the metric does not change. So the first step is that when I take dx and I map it to lambda dx is an isometry. Now I have to do the second step of my transformation. I have to rescale. So well, what I have to do is I have to go from here back to the section. But this amounts to some rescaling. Well, since it's a rescaling, you could say, oh well, rescaling means that my metric is going to be rescaled, and that's all, and then I'm done, because this is the conformal transformation. Now you have to be a little bit more careful here, because this rescaling is going to be, strictly speaking, x-dependent, right? Because I have 2 points here. I have a rescaling factor which depends on x on a certain way. So I have to be a little bit more careful. So the second step is to rescale. So there's going to be some rescaling factor, let me call it omega of x, which depends on the transformation that I'm considering. So, but I'm claiming that no matter what this factor, what this rescaling factor is, actually the derivatives of omega are not going to enter. And the way you show this is that you see how the metric changes under the rescaling. So you compute d omega of x squared. So this this involves several terms. So you have to compute omega dx plus. So omega lives on my cone. So I have x gradient omega times dx and everything squared. So this is what I need to compute. And now you see that all the cross terms which involve gradient of omega, they're going to drop out, because either they are going to be proportional to x squared, and x squared is equal to 0 because I live on the light cone, or they are going to be proportional to x dx, but x dx is also 0 because both the initial and final point both live on the light cone. So this is equal to omega squared dx squared. So the second step of my transformation involves just rescaling the metric. So since x squared equal to 0 and x dx is equal to 0. And so what I have just shown is that the metric under this transformation that I cooked up, it really changes just by rescaling. So ds squared. And so this means that whatever transformation that I'm going to be able to realize in this way is going to be a conformal transformation of the d-dimensional space endowed with this metric, which comes from the section. Right, so that's what I have just shown. So you can pick different sections, but the one section that I'm going to be interested in for the rest of this lecture is going to be the section for which this metric g mu nu is a flat metric. So I would like to have a section which I will going to call which I'm going to call Euclidean section, if g mu nu is equal to delta mu nu, and as you can clearly see, g mu nu is going to be equal to delta mu nu if this extra term does not contribute to the metric. So this is going to happen if f is a constant. So for the Euclidean section, f is going to be equal to a constant. Well, I'm going to pick this constant equal to 1. And so my Euclidean section is just given by the equation x mu, or rather x plus x minus x mu is equal to 1 x squared x small mu. So that's the section that we will need. Other sections can be useful in other contexts because they can be used to realize other metrics which are while equivalent to the flat space, like the sphere, the cylinder, and so on. And so, okay, I have shown you that any transformation that I'm going to get this way is going to be a conformal transformation. Now, what you need now to check is that in this way, I can actually realize any conformal transformation. So what I need to show you is that now, if I consider all possible SOD plus 1, 1 transformations, for example, if I consider all infinitesimal, so let me consider generators of SOD plus 1, 1, which act on the coordinates xk in the usual way, delta mk xn minus delta nk xm. So I would like to show that in this way I can generate any of the conformal transformations that we discussed. So I have to find all of my generators m mu nu, p mu, k mu, and the dilatation somewhere inside this Lie algebra of the SOD plus 1, 1. And okay, this is an easy exercise that I invite you to do, but let me tell you the answer. So the answer is this. So the identification is that up to some constant factors, g mu nu is going to be equal to m mu nu, g mu plus is going to be equal to k mu, g mu minus is p mu, and g plus minus is equal to d. So I'm not going to do all of these transformations, but maybe I'll do one. Maybe I'll just to make sure that you understand what's going on. Maybe I'm going to do this. I'm going to do this transformation. So let's do this. So how I'm going to do it? So I take this generator G mu plus, and I act with this on all coordinates of my section. So I act on this on x plus, and then I get minus x mu. I act on it on x minus, and I get 0. And once I act with it on x mu, I get minus 1/2. Well, what I get is that I get delta mu x plus, which is equal to minus 1/2 delta mu x squared. If I'm in the Euclidean section, x minus is equal to x squared, and so once you lower the indices, so I'm using here the fact that the metric, I have this matrix element G plus minus equals minus 1/2. So this explains this factor minus 1/2. And so this shows that under the infinitesimal transformation with G mu plus generator, the vector x mu, which lies in the Euclidean section, is going to go to another vector, which is going to be 1 minus epsilon mu x mu, x squared, so x minus does not change, it still remains x squared, and x mu changes by x mu minus 1/2 epsilon mu x squared. So this is the infinitesimal transformation. But now what I have to do, I have to go back to the Euclidean section. So now I have to rescale, because after this transformation, x plus is no longer 1, so I have to rescale, I have to divide by this. So let me divide by this. So I get 1. Okay, here I get something which doesn't really matter. And here I get x mu minus 1/2 epsilon mu x squared plus x mu epsilon mu x mu. And so here, what you see here is a transformation, is an infinitesimal transformation corresponding to the special conformal transformation generator up to a constant factor. So this is the form of the transformation which is expected from K mu. And so in this way, you can generate all conformal transformations, and moreover, you can also generate the conformal transformations which do not belong to the connected component of the conformal group. So you can, as an exercise, I leave it to you as an exercise to realize parity and inversion inside O d plus 1, 1. So what have we achieved? We realized all our conformal transformations in a very nice way. Eventually what we would like to do, is we would like to compute correlation functions of fields which transform under conformal transformation in a simple way. In order to do this, we have to also make our SOD plus 1, 1 to act on fields. So we have to put fields on the light cone. And we have to make this group act on fields. And so what are we going to do? So we're going to consider, so make SOD plus 1, 1 act on fields. So I'm going to consider a field phi of x, which lives on the light cone. And the transformation is going to be exactly the transformation which is appropriate for a scalar field. So x, if x goes to x prime, I'm going to consider phi tilde of x prime equal phi of x. So this is appropriate for scalar fields. Okay, now I have to solve a little problem. I know that my physical field phi of x depends on d coordinates, but the field living on the light cone depends on d+1 coordinates. So I have to find a way to make sure that the number of coordinates is the same that I started with. So the way this problem is solved is that, okay, I demand that my field phi of x restricted to the section agrees with the physical field phi of x, which is going to be a physical field in the conformal field theory. And as now I have to extend this field away from the section, and I'm going to extend it by demanding that it transforms homogeneously under dilatations along the light cone. So phi of lambda x is going to be equal to lambda to some parameter minus delta times phi of x. So you see, I'm considering fields which live on the light cone, and for some strange reason, which I'm just cooking up, I want my fields to be homogeneous under rescaling. So now, what's going to happen? I mean, you know that if you take a field of this form, and if you act on it with SOD +1, transformation, this, by construction, is bound to correspond to some representation of the usual d-dimensional conformal group acting on this corresponding field small phi of x. You just have, you are guaranteed that this is going to happen this way. You just have to work out what the transformation is going to be. And also, you know that this field, small field phi of x, is going to be characterized by some scaling dimension, delta phi. And here I'm introducing some other parameter, delta. And of course, everything is fixed in such a way that there's going to be some relation between this delta and delta phi, and in fact, they're going to be identical. So this is a little computation that you have to do. But it's basically obvious that what's going to happen is that now if you make the conformal group act on this big phi, and you see what happens with a small phi, then you recover the transformation phi tilde of x prime is equal to 1 over omega of x to the delta phi of x. In order to convince yourself that that's what's going to happen, just look at this picture that we already used when we compute the transformation of the metric. So just as it happened for the transformation of the metric, you pick a point x, you transform here, and then, as we said, so here and here the value of the field phi is identical because that's how we make our SOD +1, act on big phi. But now, to get back to the section, I have to rescale. I have to rescale by this factor omega, which, as we explained, is exactly the scale factor for the conformal transformation. And so, since our field big phi is homogeneous under such rescalings, I know that phi tilde as a function of x prime is going to be given by this formula. So it's just like everything is magically arranged to get precisely what you need. Okay, so we had to work a little bit. We introduced this formalism, and now we are going to harvest the benefits of this formalism. we are going to harvest the benefits thanks to this corollary that suppose that we use this formalism, and suppose that we manage to construct some object which I'm going to call phi delta 1 of x1, well, no, we can call phi delta 1 of x, big phi delta 2 of y, phi delta 3 of z, and suppose that I'm able to construct this object which depends on x, y, z, and on delta 1, delta 2, delta 3 in such a way that, first of all, it's consistent with all the rescaling properties of the big phis, and moreover, it depends on x, y, and z in such a way that it's invariant under the Lorentz transformations, under the SOD plus 1, 1 transformations. So if it's invariant under SOD plus 1, 1, so if I'm able to do this, then I'm guaranteed that if I take this object, so it depends on x, big y, big z. Let me take this big X, big Y, big Z, and let me project all of them to the section, to the Euclidean section. So I'm guaranteed that the projected object, let me call it small phi delta 1 of x, small phi delta 2 of y, is going to be invariant under conformal group. Okay, this is as much as I have shown. Now, if you think a little bit about it, you can actually show the converse, that any object which is invariant under conformal group, if you lift it to the cone, using basically taking this equation and reading it not from left to right but from right to left, then you are guaranteed that the object that you're going to find on the cone is invariant under SOD plus 1, 1. So this formalism, it's really like a one-to-one correspondence. So I just want to add one word of warning, is that I'm not claiming that these fields, big phis, living on the cone, they have any physical meaning. I'm not claiming that my conformal field theory secretly has one extra dimension in which my fields fluctuate or something like that. I'm just going to use this corollary as a machine, as a crank, and by turning this crank, I'm going to generate effortlessly all the correlation functions that I'm going to need in d dimensions, and I'm going to be guaranteed that the expressions that I'm going to get are conformally invariant. And in the cases where I cannot find corresponding Lorentz invariant expressions in d plus 1, 1 dimensions, it means that the corresponding conformally invariant expression in d dimensions doesn't exist. So I can prove selection rules this way, when things exist and when things don't exist.
Is there a way to lift descendant fields to the cone in an easy way?
Yeah, so the question was, what about the descendant fields? Can we also lift the descendant fields to the cone? It's as usual. You know, if you understand very well primary fields, then you can work out what happens for the descendant fields. Sometimes you have to go through these exercises. So like your question can be probed more generally. Suppose that you want to compute, you have some differential operator. Descendant field is just some differential operator in d dimensions, and you want to know how to compute the value of this differential operator in the ambient space, in the embedding space. This is sometimes important to be able to do For example, if you know you want to check if your field in d dimensions is conserved, you would like to be able to check this in the embedding space. So you have to lift the conservation operator to the embedding space. You have to check that whatever you lift to the embedding space is a good differential operator in the embedding space. So the lift always exists, but sometimes it's not obvious. It contains some extra terms that you might not immediately guess. And later on we will see some very interesting example of that. Any other questions? Yeah?
Is there an assumption on the diagonalizability of L0?
The question if there is any assumption on the diagonalizability of L0. So, so I'm working in I'm assuming that I'm interested in a particular representation of the conformal group in d dimensions, which is a very simple representation, which is a representation which corresponds to a field having a primary field having a particular scaling dimensions. So in my lecture, I discussed that in my previous lecture I discussed that the if you make certain assumptions like the theory is reflection positive and so on, then you can argue that the dilatation operator is self-adjoint and positive, and under this assumption you can argue that spectral theorem applies to it, and so it is diagonalizable. So if you want to relax those assumptions, you sometimes have to do this, in particular if you're dealing with non-unitary theories. But here I'm just considering a very simple case, where the field has a well-defined scaling dimension. Once you know that the field has a well-defined scaling dimension, the next question you ask, okay, but what is the correlation function? And I'm giving you the recipe to compute this correlation function without working very hard. Okay, so let's do some very easy computations, and then a slightly more difficult computation. So the easiest computation you can have is you can compute a two-point function of a primary field. And so you write down an expression in the embedding space. So I'm considering a two-point function of the primary field with itself. So this object that I'm writing here, you shouldn't think of it as in some probabilistic sense as I'm averaging anything. This is just a placeholder for a conformally invariant object which depends on two variables x and y and is scale invariant under the dimension, under the scaling of x corresponding with parameter delta according to that formula, and to the variable y with the same delta. And the only object that you can write down with these properties in the embedding space is up to a constant 1 over x times y to the power delta, which is Lorentz invariant. Now, if you have never seen this, expression, then you might pause a little bit and ask, okay, I mean, is it really true that it's the only object? Well, let's think a little bit about it. What are the things you can possibly write? So it has to be a function of x and y. It has to be a function which is invariant under Lorentz transformation, so it has to be a function of scalar products of x and y. Which scalar products can you write? You can write either things like x times y, or you can write things like x squared and y squared. But both x and y live on the light cone, so you can only write x times y. Moreover, you know that the function that you're going to write has to rescale under rescaling of x and under rescaling of y according to that equation, because that's our postulate. So lo and behold, this is the only function. Notice that if these two fields had different scaling dimension, delta 1 and delta 2, then I wouldn't be able to write any expression with these rescaling properties, because I would have to write something like x times y to the power delta 1 or delta 2, and none of this would work. And so this means that fields of unequal scaling dimension in the conformal invariant theory have 0 two-point functions. So this is a very simple way to see this. So now we take this formula and we would like to project it to the section to recover the physical two-point function. And so I pick x, x plus, x minus, x mu equals 1 x squared x mu, and similarly 1 y squared y mu. So now I have to compute the scalar product of these two vectors, and the scalar product x times y is equal to minus 1/2 x squared plus y squared plus x times y. And so it's equal to minus 1/2 x minus y squared. So I see that this function, if I project it to the physical space, it gives me the two-point function in the physical space phi delta of x, phi delta of y, equals some normalization constant, which I'm going to fix to 1, divided by x minus y to the power 2 delta. So it's a very easy computation. I'm sure you have seen the answer. And as always in this course, first you do something easy and it looks like it's masochistic, but now you start applying it in more complicated situations and you see that actually it's a big advantage. So let's do the same thing for the three-point function. So now let me take 3 fields. So phi 1 of x, phi 2 of y, phi 3 of z. And you have now more possibilities. So whatever you write is always going to be a function of pairwise scalar products. So you have to write it as x times y to some power alpha 1, x times z to the power alpha 2, and y times z to the power alpha 3. I mean, strictly speaking, you could have had a sum of these terms like this over different alpha 1, alpha 2, and alpha 3. That would be also allowed. But now we would like to impose the extra requirement that that this function has to rescale properly under rescalings of all x's. And so now you see if rescaling under x will come from alpha 1 and alpha 2. So you have to impose that alpha 1 plus alpha 2 is equal to delta 1, and alpha 1 plus alpha 3 has to be equal to delta 2, and alpha 2 plus alpha 3 is equal to delta 3, sorry. And so this system of equations has only one solution, which I'm not going to write down. And so this tells you that the three-point function in a conformal field theory of a scalar field of 3 scalar fields is uniquely fixed up to a prefactor. So you see here, I fixed the coefficient in the two-point function to 1, and here there's going to be some coefficient C1 to 3, which is a three-point function coefficient, which is not fixed by the symmetry, as she also mentioned. But everything else is fixed. Everything else is fixed. And now if you go to the from the embedding space, if you project to the section, so each of these things like x times y is going to give you a difference squared. And so you recover the usual Polyakov formula for the three-point function in the conformal field theory. And so what else can I say? Now, as you know, if you go to the three-point function, to the four-point function level, then the situation changes a little bit. You have at the four-point function level, you have these cross ratios u and v, and the cross ratios are invariant under any conformal transformation, and so any function of the cross ratios would be conformally invariant. Now, you know that the conformal cross ratios, if you want to check that they are invariant under conformal transformations, there's a little computation that you have to do. But if you work in the embedding formalism, it's obvious that they're going to be invariant under conformal transformations. Because let me write in the embedding formalism what U is. U is equal to x1 times x2, x3 times x4, divided by x1, x3, x2, x4. So this is the expression for you in the embedding space. Now you see that this expression is invariant under rescalings of x1, of x2, of x3, and of x4. So it's completely invariant under rescaling of any of the four vectors. And in addition, it's also Lorentz invariant because it's only written in terms of scalar products. So you know right away, without doing any computation, that if you take this expression, if you project it to the section, you're going to get something which is invariant under conformal transformations. So if you work on the embedding space, the existence of conformally invariant cross ratios is not a mystery. It's like straight out in your face. Okay, so what else should I say? You can take this formalism and you can extend it to fields with spin. I'm not going to discuss this. This is just some technical work. Instead, what I'm going to discuss, something a bit less standard, is how to use this embedding formalism to compute the conformal OPE. So this will give me also a chance to talk about conformal invariant OPE. But before I go on, any questions? Yeah.
What happens when you set d equals to 2? I mean, can you see divergence real imaging this?
So the question is whether I can use the embedding formalism also in d equal to 2. You can use it also in d equal to 2, but you will only be dealing then with the global conformal symmetry group. Yeah?
What about the epsilon tensor and some like I don't know, you have 4 variables, x1, x2, x3, x4,
So Max is asking about the epsilon tensor. Yeah, the epsilon tensor is, it makes perfect sense in this formulation. You can also lift the epsilon tensor to the embedding space. It is a SO invariant object, so everything's fine. You also recover conformally invariant structures involving the epsilon tensor. Okay. So let's talk about the conformal OPE. So we already talked about OPE, and as I said, you put any two operators inside the sphere, and then you take the product, phi1 of x1, phi2 of x2. Yeah, now I'm forgetting about the embedding space for a while. I'm just writing things in the physical space. And then the conformal OPE is going to take a form. It's a formula also that she wrote in the 2D context. So they're going to be this OPE coefficients, phi1, phi2, O. And then they're going to be a sum for each operator O, for each primary appearing in the sum. They're going to be a sum over derivative orders alpha. They're going to be some function, the alpha, which depends on x1 and x2. And they're going to be the derivatives of the operator O sitting at 0. So, and as she said, and as I confirm, which is valid also in d dimensions, this function is fixed by conformal symmetry. And the only thing which is not fixed by conformal symmetry are the dimensions and spins of operators which appear in the OP, and the OP coefficients are not fixed by conformal symmetry. So in order to fix these coefficients and the dimensions, you have to impose the bootstrap, you have to impose crossing symmetry. But what I would like to discuss now is how to fix this. I would like to convince you that these functions B alpha are really fixed by conformal invariance, by conformal symmetry. And okay, there are various ways to do this, to get convinced in this fact. And one way to get some confidence that this fact should be true is to compute the 3-point function. So if you compute the 3-point function phi1 x1, phi2 x2, and I insert some operator O at the point x3, so this 3-point function is some known function of x1, x2, x3, as I just explained. It's given by the projection of that expression to the physical space. But on the other hand, I can compute this 3-point function using the OPE, and so it's going to be equal to C phi1, phi2, O, sum over alpha, B alpha of x1, x2, and here you will have D alpha O of 0, O of x3. And so since this is known, this 2-point function and its derivatives are also known, this gives you, at least in principle, a way to work out this coefficients B alpha. So you can work out. At least in lower orders you can do this computation. And okay, well, you see that it works, but it's a bit painful. So but at least you get confidence that this must be true. So I would like to, and since now we know about this shiny embedding formalism, I would like to give you another way to do this computation, which is much more elegant.
Work out the alphas even though they're appearing in the sum because you have this x3 here. Is that there?
Yeah, so the question was, is the reason that I can work out B alpha is because I have x3. Yeah, that's precisely the point. So I know this. I know that this OPE should work for any x3. So I have this x3 parameter, and this allows me to fix these coefficients order by order. But let me try to do this computation in a different way, which is manifestly conformally invariant. So the idea is this. So I showed to you that you can lift conformally invariant correlation functions to the cone, to the embedding space, and this allows us a very simple way. We are sure that all our calculations are manifestly conformally invariant in every step. So can't we do something similar also for the OPE? So we know that our OPE has to be conformally invariant, so can't we also lift the OPE to the cone in the embedding space? That would be really great. Well, let me try to do it. So I'm looking for an expression of the form. So I have two fields which live on the cone, phi delta 1 of x1, phi delta 2 of x2. And I would like to write an OPE. And for simplicity, let me assume that the field in the right-hand side of the OPE also lives at the same point as one of the two fields on the left-hand side. This is just a particular case. There's no loss of generality here. So I would like to write something in the right-hand side which is conformally invariant. And okay, what I'm going to write, let me first write it down and then I will explain. So I'm going to write here x1, x2 to the power alpha. And then I'm going to write here a certain differential operator d1, 2, which I'm going to raise to the power h. And okay, now I'm just taking this out of the box, but believe me, it can be really worked out systematically. I'll explain why. So this operator d1, 2 is going to have the following form. x1 contracted with the derivative in x2 direction times d minus 2 plus 2 x2 times d2 minus x1, x2 Laplacian on the cone, d2 squared. Now, well, this looks rather complicated, so let me explain where this comes from. So, okay, what is special about this differential operator that I'm writing down? There are two things that are special about it. Like the first thing that you can easily see from here is that, okay, for any differential operator on the light cone, you can ask what does it do with the scaling of the functions on which it acts. So we know that it's very important to keep track of how the functions rescale under rescaling of x. And you see that this operator has two derivatives. Then you get multiplied by x2. So it has scaling 1 in the x2 derivative, and it has scaling minus 1 in the x1 direction. So scaling minus 1, 1 in x1, x2. So this is the first thing about this operator. And if you look at this term here, it also respects this scaling. So so this operator is homogeneous, x in x1 and x2 in a homogeneous way. So that's the first thing about this operator. Now there is another interesting thing about this operator, which is absolutely necessary. And so this comes back to the question about the differential operators in the embedding space. So when you are in the embedding space, you are acting with your differential operators on functions which are defined on the cone. But now you can start to be worried, because you see my function is only defined on the cone, but I have, for example, here the derivative with respect to x2. Well, I can take the derivative with respect to x2 in any direction. Some of the directions are going to be along the cone, and other directions are going to be perpendicular to the cone. So in order to compute the value of this differential operator, I have to extend, strictly speaking, my function away from the cone. And this extension is not unique. There are many ways to extend the function away from the cone. So in order for our computations to make sense, we have to demand that our differential operator is interior to the cone, which means that it does not depend, the value of the differential operator should not depend on how you extend the function away from the cone. So this is a very special property of this operator d1, 2, that if you take d1, 2 and act with it on some function f which lives on the cone, this does not depend on how you extend. And so how can you show this? So this I leave you as an exercise. What you have to show is that any extension that you can possibly come up with, so any two extensions, you take two extensions, they have to agree on the cone. It means that they are proportional, since the equation of the cone is x squared equal to 0. It means that the two extensions, any two extensions, are going to have the form, are going to differ by x squared, x2 squared, which is the equation of the cone, times some function of x2. So these are this is the difference between two different extensions. And so what you have to show, if you take d1, 2 and if you act on this on this formula, then you get 0. You get 0 after you get 0, of course, when you set x2 squared equal to 0. So you take this function, you act with d12, then you go back to the cone, and you should get 0. This is the claim. So this is something that you can check. It's an easy computation, and interestingly, an operator with such properties does not, a first order operator with such properties does not exist, but a second order operator with such properties exists. So that's why I'm using the second order operator. Yeah, a second order operator with such properties is unique. Okay, so that was something interesting. And now I would like to take this operator and I would like to use it for my conformal OPE. So since the operator is defined on the cone and it's written strictly in an SOD plus 1, 1 invariant way, whatever I get using this operator is going to be conformally invariant. But there is a little problem. The problem is that I have to make sure that that equation that I wrote down, it is consistent with scalings of all involved fields. So I know how phi1 rescales, I know how phi2 rescales, I know how O rescales. So for this I have to impose the following conditions. So scaling fixes that delta plus h plus alpha has to be equal to delta 1, and minus h plus alpha has to be, no, this is delta 2, has to be equal to delta 1. So from here you determine alpha and h, and you get, so you get alpha equals delta 1 plus delta 2 minus d over 2, and h is alpha minus delta 1. And so here you have a little conceptual difficulty because you realize that this value h is in general non-integer. And so what we are instructed, that formula is nice, but what we are instructed to do by that formula is that we are instructed to raise the differential operator to a non-integer power. Now this may look like a worrisome thing to do, but actually, I mean, in general it is a worrisome thing to do, but in our particular case this is not at all a problem, and the reason is that we are only interested, so we are trying to work out the OPE. OPE is going to have an expansion in powers of x1 minus x2 times the derivatives. And so what we should take a look at what does that operator do in the limit when x1 equals x2. So let me compute d12 in the limit when x1 equals x2. So in this limit, the last term drops out because it's proportional to x1 times x2, which becomes 0. Now the first term simplifies dramatically, so the first term becomes x2 d2 d plus 2 d minus 2 plus 2 x2 d2. And so so if you take this operator x2 d2 and you act with it on a function which is scale invariant as OD is, so this gives you minus d minus delta times d minus 2 minus 2 delta. So it gives you a number. It gives you a number, and this number is in a unitary conformal field theory because of the unitarity bounds, which unfortunately I didn't have time to discuss last time, but you can read about them in the notes. This expression is just some positive number. And so what this shows is that this operator looks like some positive number plus corrections that are going to go to 0 when x1 becomes equal to x2. And so this gives us hope to actually take this operator and raise it to a non-integer power. So the way you do this computation is this. So you take our cone, and so we have a section. On this section we have a function O delta of x. And now we extend this function to the full cone. So on the full cone I have I can introduce this coordinate k, which is the rescaling parameter. So k times 1 x squared x mu. So I have a function O delta of kx, which is equal to k minus delta O delta of x. And so I have to write down what my operator does when it is applied to this function. And so this is a little computation that you can try to do by yourself. But so in other words, I'm projecting my operator down to the section. And so when you do this calculation, you find that d12 is equal. So I already wrote down there. So it's like minus delta plus plus x12 mu d2 mu. Then this factor, which is d minus 2 minus 2 delta. And then finally the last operator becomes equal to minus x12 squared over 2 Laplacian d2 mu squared. And so what this equation means is that my operator projected down to the section, it looks like a constant plus some terms which are of the order x1 minus x2. And so now, of course, I can take this operator and I can raise it to any power, because so what I'm dealing here is that I have to compute things like 1 plus O of x to some power h, and this is just a Taylor series. So you have to take this Taylor series, you can take it to an arbitrary order you wish, and the claim is, since our construction was manifestly conformally invariant, if you do this calculation, you will generate the full operator product expansion, and it's going to be conformally invariant in the d-dimensional space. Yeah.
To define the action of B as like the integral over like the kernel of this differential operator with some like non-integer powers.
So the question is whether I can define this operator d12 as some sort of an integral as opposed to a formal power series expansion. What I know you can, so here I kind of presenting to you the blueprint. So I would like to convince you that this computation can be done. But of course, if you do it the way that I describing it to you, you still have to do this power series expansion, and okay, you can do it to any order you wish, and you know that you can generate a series to any order you wish, but it's not going to be, you're not going to get this way an explicit expression for the coefficients of the expansion. So you will have some series. So I actually know a paper where this idea comes from. It's an old paper of Ferrara, Gatto, and Grillo. Which was from the early period of conformal field theory. It was around 73, 74. So And in that paper, they actually do what you're suggesting, so they're deriving some sort of integral formula that gives you a way to compute coefficients of this expansion as integrals. So this can be done, but okay, this requires some extra work. Any other questions? Well, if there are no further questions, I actually would like more or less to conclude at this point with a short philosophical discussion. So these were supposed to be lectures about conformal field theory and the bootstrap, but I have talked about many things which are useful to the bootstrap, but I didn't actually get to talk about the bootstrap itself. There was simply not enough time. But okay, you can probably pick up a lot of bootstrap philosophy and also some more than just philosophy from the lectures of Sheehan in the two-dimensional context. But much of two-dimensional bootstrap philosophy applies also in higher dimensions. You just have to believe that you will succeed and start doing the calculations. So Tom de Grand in his yesterday's lecture did some publicity to the bootstrap results, for which I thank him. So as Tom reminded us, according to Fermi, there are two ways of doing the calculation. There's you can either have a clear physical picture or a rigorous mathematical formalism. And in my personal opinion, in conformal field theory you have both, but I leave it up to you to judge. Thank you. So the question is, if you try to do crossing, where do you do crossing? Do you do it in the embedding space, or do you do it in the physical space? And is there any advantage to go to the embedding space when you do crossing? So, in my personal opinion, embedding space is just a kinematics machine. It's just a smart way to generate for you expressions that you know are going to be conformally invariant. Now, crossing is something which is intimately related to locality. Locality is visible only in the physical d-dimensional space. So, in my opinion, when you do crossing, you always think in the d-dimensional space. Now, said that, when you do crossing in the d-dimensional space, there are some conformally invariant objects that you have to compute, which are called conformal blocks. And there are various techniques to compute these conformal blocks, various smart ways to compute these conformal blocks. And when you compute conformal blocks, you are allowed to use whatever weapon you have at your disposal. In particular, you're allowed to use the embedding space if you find that useful.
Is it always possible to extend the embedding formalism for superconformal group?
So the question was about the embedding formalism for the superconformal group. Whether it's always possible. I definitely know that it's very often possible. In many cases that I'm aware of, it's possible. Whether it's always possible or not, I would think that it should always be possible because it basically amounts to saying that if you have a superconformal group, that it has some nice representations on which it acts linearly. And since any finite dimensional supergroup has such representations, I see no reason why appropriate version of the embedding formalism cannot always be derived. Yeah.
When you have like some kind of weakly broken conformal symmetry, is there a natural way to understand
So there was a question about weakly broken conformal symmetry and whether you can understand weakly broken conformal symmetry in the embedding space. Well, this would require us to discuss what weakly broken conformal symmetry means, and maybe we should discuss this offline. I'm not sure.
Do you run into trouble when your field is close to the unitarity bound with this expansion?
So, as Max points out completely correctly, it looks like so in order to argue that I can take this operator and I can raise it to the non-integer power, I had to take advantage of the fact that the leading term in my differential operator was a constant which was non-zero. Now that constant goes to zero precisely when the operator delta approaches the unitarity bound. So what does this mean? Is this a sign of some pathology, or is this a sign of things that we would expect to exist but we are not able to compute? So actually this is not pathological at all. This is very physical. So if the field delta approaches the unitarity bound, so it becomes a free field. In this limit, the free field is a very special field. It cannot couple to anything. It cannot appear in any UPE that you might wish. It can appear in the UPE of other fields which also live in the same free theory. For example, if you take a field phi, it can appear in the UPE of, say, phi to the fifth with phi to the fourth. It can appear in the UPE. You know that it has to appear in the UPE of fields of dimension 4 and 5, but it's not going to be expected to appear in the UPE of fields with the dimension square root 2 and square root 3. And so if the field delta lives at the unitarity bound, we don't expect that this conformally invariant UPE should always exist. It should exist only for very special values of delta 1 and delta 2. And so this is what we are seeing here. We are seeing that generically this formula is going to become singular, but in the limit for very special values delta 1 and delta 2, you should still be able to find this differential operator.
Is it possible to generalize that formula to operators with these things?
So the question is whether it's possible to generalize the conformal PE formula for the operators with spins. Yes, it's possible, and in fact it was done in this paper by Ferrara, Gatta, and Grillo.
In that case, there are again zeros when the currents are conserved.
So what happens with the unitarity bounds in this formula for the operators with spins? I'm not sure. I would have to check, but I guess I see no reason. Logically it should happen as well. This difficulty, because the conserved current operators, we also know that they can only couple to very special external fields.
Can you choose a different scaling to avoid this problem? Like I imagine the -1,1 scaling is not very important as long as you can solve the set of equations.
So the question was if there is some other magical way, some other magical differential operator which avoids this problem. I think not, because as I explained, this problem is very physical. We know physically that the free scalar simply is not expected to couple to fields with other dimensions. So I would expect that if you find some other workaround way, then it should the problem should manifest itself. The same problem should manifest itself also in that way.
All right, well, if we have more questions, we could ask after. Let's thank Slava one more time. Before we go to lunch, I have 2 lost objects. Is there anyone here named Susmita Saha? Okay,